The function is z equals f of xy is x to the fourth minus 2x squared plus y cubed minus 27y minus 15. I want to find local extreme points, relative extreme points of this, with the same process as Calc 1, except generalized. In Calc 1, you took the derivative, set it equal to 0, solve for x to find the critical points. Then you test, do those critical points give you a max or min or neither? There's a first derivative test and a second derivative test. Here we do the same thing, except we take partial derivatives. We set them both equal to 0, solve the resulting system of equations, and we only use a second derivative test, not a first derivative test. We look at the sign of the second derivative effectively, not quite, but almost. Instead of thinking about whether the first derivative changes sign from positive to negative or something like that. I don't know if you remember that from Calc 1. Might have made number lines and marked off where it's positive and where it's negative, that kind of thing. Right, so what are the partial derivatives here? dz dx, or fx if you prefer, be 4x cubed minus 4x, which you should probably factor. It's almost always a good idea to factor things as much as possible, because you're going to be setting these things equal to 0 and solving for x and y. Partially, what makes this a little easier than it might be in general is that these derivatives are in the end functions of one variable, so that makes it a little nicer. Once again, factor as much as possible. Sometimes you might have to use the quadratic formula, but in this case, we can factor. Set these both equal to 0 and solve the resulting system of equations. As I just said a minute ago, in general, it's possible both equations could involve both x and y. It could be a nonlinear system of equations to solve for x and y that could be pretty challenging to solve. But in this case, it's not too bad. You see that here, x is 0 or 1 or negative 1, and here y is 3 or negative 3. That actually results in 6 critical points for each combination of those. X is 0, y is 3, x is 1, y is 3, x is negative 1, y is 3, x is 0, y is negative 3, x is 1, y is negative 3, and x is negative 1, y is negative 3. We want to classify these. We want to use a second derivative test to classify it. Do I look at the sign of the second derivative? Sort of. You need to take second derivatives, but there's more than one of them. fxx is 12x squared minus 4. I'm going to put these in a certain pattern here. fxy, let's put that to the right of that. Differentiate this with respect to y, you get 0. fyx, the other mixed partial, it has to be the same thing. 0, and it is. And fyy, differentiate that, you'll get 6y. You don't have to do this, but you can think of this as a matrix. You don't have to do that, but you can. And you can write down something called D, which is the determinant of this matrix. However, it's not typically called a determinant in this context. It's typically called a discriminant. Still starts with D. It is the determinant of this matrix, though. It's fxx times fyy minus fxy times fyx, though because of the fact that fxy and fyx are the same, I can write that as a square of fxy. How does this simplify for this example? It simplifies to just multiply these. 6 times 12 is 72 x squared y minus 24y. for this example. Might be simpler to write that as 24y times 3x squared minus 1. Not that you have to. Then you take this discriminant and you plug in the critical points. It discriminates the types of critical points that you get. If when you plug in a critical point, you get a negative discriminant, that means that critical point is neither a max nor min, but something called a saddle point. That if you looked at the graph, you could sit on it like a saddle. I'm talking about the three-dimensional surface. That's the graph of the function. It's called a saddle point. It's a max in one direction and it's a min in another direction, if d is negative. If d is positive, then the critical point is either a max or a min, but you have to do something else to figure out which. So let's try some of the examples here. What's d evaluated at 0, 3, for example? You plug in critical points here. 0, 3 was the first critical point. You don't plug in other points, just plug in critical points. X is 0, y is 3. If I use the second formula, I get 24 times 3 times negative 1. Negative 72. But the important thing is that it's negative. That means 0, 3 is a saddle point. Next critical point, 1, 3. You get 24 times 3 minus 1, which is positive. So it's not a saddle point. Is it a max or a min? Plug the point into fxx as well to figure out if it's a max or a min. If you do so, fxx is 12x squared minus 4. You get 12 minus 4 is positive. Effectively, what that ends up meaning is the graph is concave up near the point. It's a min. You might say, well, it's concave up in just the x direction. But it turns out it'll be concave up in the y direction as well. If you had plugged this point into fyy, you also would have gotten a positive number. It's good enough to just plug it into one of them. This means, these two things mean 1, 3 is a local min or relative min. Let's try the next one. The next one was negative 1, 3. That also gives you a relative min because it also gives you the same value of d and same value of fxx. Why? Because of the squaring involved. Because you got x squared there. Notice that fyy would still be positive because the y coordinate is positive. Negative 1, 3 is also a local min. It's got 3 more points. D of 0, negative 3. Plugging into D here. 24 times negative 3 times negative 1, positive. That's something different than happened with 0, positive 3. If I plug this into fxx or fyy, I get a negative number. That means 0, negative 3 is a local max. The negative fact there effectively means the graph's concave down near the point. So you get a local max. D plus or minus 1 comma negative 3, maybe are both the same. Yeah, and in both cases, you get a negative quantity. Those end up being both saddle points. Are saddle points. I'll let you check that. Let's end class by seeing if we're right by a graph. Contour plot of this function. What's the function? X to the 4th minus 2x squared plus y cubed minus 27y minus 15. The minus 15 doesn't really make much of a difference for the locations of the maxes and mins. Does it seem like we're right? Hard to completely tell. Looks like this, so it's darker up here, so it's close to minimums up there. And in fact, at the two eyeballs, so to speak, that's probably where there's a minimum. These two, -1, 3, and +1, 3. And in the middle, at the nose, probably a saddle point, 0, 3. Down here, the maximum, the lightest part, is supposed to be at 0, -3. These are supposed to be saddle points, which seems reasonable since they got kind of curves that are not circular near these points. You'd have to zoom in there to believe it more clearly.